right, I think we're going to go ahead and get started because we have a lot to cover in the next 90 minutes, and we'll let people join as they're able. Welcome, everyone. I'm Mary Johnson, manager of 401 TechBridge. We're glad to have you all with us here today to talk about the 401 TechBridge and our new Materials Innovation Challenge. There is an amazing amount of R&D happening in composites and textiles and advanced materials and technology here in the region, happening with companies at the University of Rhode Island and at other institutions throughout the region. What we learned from Polaris and RIMTA and the Rhode Island Textile Innovation Network and the Composites Alliance and a lot of other partners, the Business Engagement Center, a lot of other partners along the way, is that companies were not connecting to opportunities in a hugely efficient way. There were certainly a lot of you who were making opportunities happen, and we thought that we had a plan to see those gaps and to create the 401 TechBridge to help bring players together and literally act as a bridge between the innovators and the appropriate entities to help you identify projects and funding opportunities and link organizations and companies with technical skills that they need to find solutions. The goal of today's webinar is to introduce you to the 401 TechBridge and our first funded research opportunity, the Materials Innovation Challenge. In the next 90 minutes, you're going to meet the faculty at the University of Rhode Island who are collaborating with 401 TechBridge on this program. And you'll hear from a panel who will share their expertise of supporting successful projects at URI, and you will learn about the process to apply for the Materials Innovation Challenge program. The 401 TechBridge, companies tell us, and several of you on this call today have already told us, that one of the things you value about the 401 TechBridge is that we serve as a super connector. We are always on the lookout to help companies find new projects and business opportunities, and to find funding to support projects so that you can continue to innovate and grow. We bring together innovators in the composites, advanced materials, textiles, and technology fields from business, government, and academia to share ideas and find ways to spin off research and technology into commercial uses. Whether you are a startup or you're a company that needs to start developing prototypes for a product that you're developing or a technology you're developing, or you're an established company who has been looking to move into new markets, we have ways to help make the process of development and commercialization of technology faster, easier, and more collaborative. The 401 TechBridge, as I mentioned earlier, builds on the collaborative relationships that were previously developed by Polaris MEP, the Rhode Island Marine Trades Association, the Composites Alliance, the Rhode Island Textile Innovation Network, the Rhode Island Commerce Corporation, and the URI Business Engagement Center. And we continue to build on that network and create new opportunities and new partnerships. 401 TechBridge was the first entity to partner with the Naval X TechBridge initiative, and we are the hub for the Naval X Northeast TechBridge. We help manage their programmatic opportunities, and we build partnerships to engage innovative small and non-traditional businesses in the Navy's focus areas, which are maritime composites and textiles, undersea vehicles, sensors, and technologies. We also help companies find dual use and commercial applications for solutions they have developed for the Navy. Our collaboration with NUIC is now a national model for the Naval X TechBridge initiative, and our relationship with NUIC serves as a model for the relationships that we're building with our other partners, whether in defense or beyond, including the federal labs, companies who are innovating with advanced materials and technologies, whether that be national defense, infrastructure, alternative energy, automotive, healthcare, or any other sector. What I would like to do now is introduce the people who will be presenting today. If each of you could wave or raise your hand so that we can let our guests associate names with faces, that would be helpful. Dr. Arun Shukla is the Simon Ostrich Professor and Co-Director of the National Institute of Undersea Vehicle Technology, in the Department of Mechanical, Industrial, and Systems Engineering at the University of Rhode Island. Helio Matos is an Assistant Professor of Mechanical, Industrial, and Systems Engineering at URI. Sumanta Das is an assistant professor of civil and environmental engineering at URI. Dr. Shukla, Matos, and Das will be providing an overview of their labs and their capabilities and a little bit about how they have worked with companies in the past to promote and advance technology. Catherine Hazard-Flynn is the Executive Director of the University of Rhode Island Business Engagement Center, which connects companies with the resources of the university. Christian Cowan is the Chief Operating Officer of the University of Rhode Island Research Foundation and the Executive Director of the 401 Tech Bridge. Susan Daly is the Vice President of Strategy for the Rhode Island Marine Trades Association and the Rhode Island Composites Alliance, and serves as a strategic advisor to 401 Tech Bridge. And Eric Goetz is the founder and chief technical officer of Goetz Composites, and in many ways a poster child for the role 401 Tech Bridge can play in advancing, helping companies grow and build their technology. Catherine, Christian, Susan, and Eric are panelists who will talk more about advancing technology and collaborating with URI. I would like to thank all of our presenters for being here today, and we look forward to hearing from all of you. As we move forward with the agenda, Susan, could we bring up the slide deck? Thank you. 401 Tech Bridge has funding available to help businesses partner with the University of Rhode Island to further advanced materials research, testing, and validation. This is a program we call the Materials Innovation Challenge. The Materials Innovation Challenge is a competitive program that supports projects with the University of Rhode Island's Dynamic Photomechanics Laboratory and the Multiscale and Multiphysics Mechanics of Materials Research Laboratory. Companies are eligible to receive up to $35,000 toward a project with these labs at URI. Awarded projects will begin in early 2021 and will utilize the faculty, students, and facilities of the university. I'll go over the details of the application process later in the webinar, but now I'd like to turn the screen over to Dr. Shukla and Dr. Matos of the Dynamic Photomechanics Lab and to Dr. Das of the Multiscale and Multiphysics Mechanics of Materials Research Lab, who will talk more about their expertise and facilities. I'm going to let each of them introduce themselves in more detail. As I said earlier, if you would please enter your questions in the chat field. You can direct them to the whole group if you're comfortable doing that, or to me, Mary Johnson, individually, if you would prefer to keep your company name private. And at the end of the event, we will have time for Q&A. The slide deck and a recording of this webinar will be available on our website by Monday next week. Dr. Shukla and Matos, if you could please let Susan know when you need to advance slides, that would be very helpful, and I will turn it over to you. Professor Shukla is muted. Susan, can you do that without giving up your screen? There he goes.
Okay, I guess. Now you can hear me?
Yes.
Good. So thank you very much, Mary. Let me start by saying that it is indeed a great pleasure for all of us here at URI to be a part of this Tech Bridge. And Mary has asked me to stay brief and take about 10 minutes to say a few things about our research facilities. The plan is that I will probably talk for about 8 to 10 minutes, and then Helio will present after that for about 8 to 10 minutes, and then Sumanta will come after that. Our lab, the name of the lab is Dynamic Photomechanics Lab. We have almost 40 years of history. It was established in 1981. And over this time period, we have been extremely active in conducting research on materials of all different types, particularly composite materials. These composites include glass fiber composites, carbon fiber composites, Kevlar composites, We have not done a whole lot with the Dyneema or the Spectra fibers, but if a need arises, we can certainly work on those fiber composites also. The other exotic materials that we have worked over the years are functionally graded materials, metamaterials, multifunctional materials, and materials of other different types like ceramics, rocks, sand, metals. So those are all standard materials, but we have a vast experience working with materials. Our research has been funded over the years by several different agencies. Two of them stand out who have been consistent supporters of our research. One is the National Science Foundation. They've supported our work for 36 consecutive years. Then Office of Naval Research is the other big one. And at present, I would say 90% of our funding comes from Office of Naval Research. We have had funding from Air Force Office of Scientific Research, Army Research Office, Department of Homeland Security, Federal Highway Administration, and a large number of other federal organizations. We have also had funding from industry to support our work, although I'll say that the funding from industry has been small. It's not comparable to what we have obtained from federal agencies. But many companies, TPI Composites, we have worked with them, Textron, Goetz, we have done some small projects with them. We have a project right now in the lab working with Eric. Then companies in the local area in Rhode Island, Raytheon, Electric Boat, and all these companies have been involved in projects in our lab. Our expertise primarily in the lab is in experimental work, although we do numerical simulations in our lab also. And now with the addition of Helio and Sumanta, we have expanded that numerical simulation capability. But over the years, we have been, our primary expertise has been in experimental work. We also do a lot of analytical work, and that analytical work actually feeds into both the streams of experimental work as well as the numerical simulations. So the basic, we do conventional work like testing of materials at quasi-static loading conditions. You talk about tension, compression, bending, those kind of things. But that is routine. We don't consider that as part of our challenge here or research. Our focus mostly in the lab is on looking at materials under extreme loading conditions. Now, these extreme loading conditions could be extremes of pressure. So we will study materials under ambient conditions, under deep sea water conditions. So you have large hydrostatic pressures on these materials. We study materials under extremes of temperature, all the way from -50 degrees to 1000 degrees. So we can cover conditions in the Arctic as well as a hot engine type of temperatures. At the extremes of loading rates, so the quasi-static loading rates are, as we know, very, very, very slow, 10 to the power -5 per second type of loading rates, all the way to loading rates that will kind of simulate asteroid impacts. So the 10 to the power 6, almost 12 orders of loading rates we can cover in our lab. So that way, from that point of view, I think our lab is unique. One of the very, very few facilities in the country as well as in the world, I would say, where we conduct experiments under these extreme mechanics conditions. So with that small background, I would like to move on to the next slide. So the next slide here, this is my website, but I think the next slide should be a shock tube facility. Yeah, this one here. So this is one piece of equipment that actually was developed in our lab with funding from Federal Highway Administration some years back. And it simulates a very high rate of loading. So it's like similar to what you would get in case of an explosive. So this shock tube, this long barrel that we have here, this can provide controlled loading. So instead of using something like an explosive, we can control the pressure pulses generated by this, and then we impart these pressure pulses at this end here on composite materials. A lot of these materials are either plates of composite materials or sandwich structures that have face plates and the core made from polymeric materials. They could be foams or some other material. So this is unique. Now this facility that we have is being used extensively right now, but over the years we have use this to impact these targets at a variety of temperatures. So this chamber that you see here can be controlled in terms of temperature, going all the way from, as I said, from Arctic conditions to very high temperatures. In the next slide that we have, this is a video. I hope it runs here. I'll show you this. I think in this video here, this is a shock tube that is on the right-hand side. This target is a sandwich composite that we were studying for. Two companies were involved here. One was Material Science Corporation and then the Treatex Corporation in North Carolina. Material Science Corporation is in Pennsylvania. And we were looking at how we can improve the performance of such sandwich structures for naval applications. I'm not sure whether we can run this video there from control. I think if you click on this image, it should run. Yeah, just click on there, it should run, okay. So you'll see a shock coming from the right-hand side. You see this glow here and this thing, shear cracks forming, delamination, and this, finally the sandwich structure falls apart. But I wanted to point out here is that, when the shock comes and hits this target, you have very high temperatures. That's why this air ionizes and begins to glow. But with these high-speed photography that is incorporated in here, we can really probe the structure in a lot of details and try to design it. Actually, we designed a structure finally with funding from ONR and for these companies that is probably one of the best I think I have seen around the world. So with this, let's go to the next slide. So this one here is a slide that kind of shows our capabilities in terms of probing these structures. We are experts in looking at these structures using non-contact techniques. These are mostly optical techniques. Yeah, these are interference-based techniques, or the technique that I'm showing here is what we call the digital image correlation technique. We photograph this target here with high-speed cameras. These two cameras just serve like your eyes, the stereo vision of this target, and then we use the information from here to get properties of this material that are of interest to us in designing better sandwich structures. So these properties could be displacement, strains, velocities, and things of that nature. So we have in our lab some of the highest speed cameras you can think of, cameras that can take 200 million frames in a second. We bought a system of cameras recently that can do 10 million frames per second at very high resolution. So we have those kinds of capabilities in the lab to really do unique type of work for our defense agencies, particularly Homeland Security, ONR, and Air Force are interested in this kind of work. We go to the next slide, please. So here is a facility that, same facility, the shock tube facility. This time we are using a target at very high temperatures. So this target is at about 1,000 degrees Celsius. You see it glowing, red hot. So this work was done for Air Force Office of Scientific Research. Similarly, we can create low temperatures also in our facilities here. Okay, we'll go to one more, next slide. Now, this shock tube that you saw just now shows loading in air. Now, this is an underwater shock tube. So here we can put targets underwater. This is water filled, and we introduce a shock at this end by impacting with a striker, and that creates a shock traveling in this direction. And we probe the structures. We have this facility also. We are currently using this facility for studying materials for the Office of Naval Research and Naval NUIC here. But we also have a project from the Medical Research Facility of Navy that is looking into soft materials here. These materials could be foam materials or could be biological materials like tissue and hydrogels and things like that. Next slide, please. So this facility we are extensively using for looking at structures underwater at high pressures. This is a pressure vessel that can generate 1,000 psi of pressure. We can also use explosives in here along with the pressure loading to look at the structures underwater. We have high-speed cameras incorporated in this pressure vessel. These things really make this vessel unique. I don't think there is any other vessel of this kind that I'm aware of that can do underwater testing of these structures for dynamic loads and incorporates optical methods like we do in probing these structures. So if you go to the next slide, you will see that a little bit better. Here, so this is an image of an implodable, and Eric would appreciate this. This is a tube made of composite material that as you increase the pressure, take it underwater deeper and deeper, it implodes. And with these dots that you see here, these help us in probing the structure in real time and then help us design these structures in a better way. I'm going to stop at this point and let Helio take over from here, okay?
Hello. Hello. Hello, everyone. I'm glad to be here. Can you hear me? All right.
Yes.
Great. So I'm just going to continue the discussion that Arun Shukla started, and I'm going to talk about some of the facilities, additional facilities we have in the dynamic mechanical photodynamics lab. This one that is shown on this slide is the split Hopkins pressure bar. And what this does is it allows us to test the specimens under very high strain loading conditions. This is the facility that was mentioned earlier that we could get up to 10 to the 6 strain rate. These are conditions that mimics the rate of loading of asteroids. What it's shown here is a specimen in compression between 2 bars. So we have a striker bar that sends a pressure pulse that interacts with the specimen that is sandwiched between the incident and the transmitted bars. But we also have the same pressure bars that can do tension and torsion experiments. In addition to that, we can have specimens being cooled or heated between negative 40 Celsius and 1,200 Celsius for metallics. And in this next slide, we are showing one of our newest facilities. This is an impact tower tester. This is the stock photo, but the facility we have in the lab also has an environmental chamber within the striker. This is for compression testing, and we can move the striker between 1 and 20 meters per second. And we can do temperature testing between negative 40 Celsius and 150 Celsius. So the entire environmental chamber would be within that temperature. And in the next slide, this is an image of one of the previous projects we had with the Army, where we're designing armor material. So the material that is shown here, though in not great detail, is a composite with a sandwich core. And what you're seeing is a still image of the bullet right before it makes impact with the composite. So we also have the capability of doing ballistic experimentations in the lab. And in the next slide is our 2 weathering facilities. The first one shown in the left is a ultraviolet weathering facility. So we place our material in there to simulate exposure to sunlight at an accelerated rate. The acceleration rate depends on the specific material that we're testing. But what we can also do, shown on the right, is accelerated weather through water infusion of salt water. And this diagram here, we have a multitude of variations of this facility. The one that is shown here is just for, we place the specimen in a saline solution. Typically, we have it at 3.5% sodium chloride, which is about the average salinity of the oceans around the world. And we have heaters that heat distilled water to keep the saline water at a constant temperature. So the temperature that we set this to depends on the material. So typically we will stay below glass transition. So we are not changing the mechanical properties by introducing very high temperature. At the same time, we want to be as high of a temperature as we can below this transition zone so we can get higher acceleration rates. In the past, we were able to achieve acceleration rates of 5 to 10 years for about a month of soaking. So two things happen when we soak the material in saline water. The first one is the material will absorb water, so it can swell up, and that in itself can cause some pre-stresses if we have some around the boundary conditions of the specimen. The second thing is the interaction between the material and the salt water can cause degradation in the mechanical properties. So we observe these two phenomena for the materials that we're interested in. And on the next slide, we have another variation of the saltwater weathering facility shown here. And what this is, we have the same saltwater bath, and this large stainless steel canister is where the specimen sits inside of is pressurized. So now we're introducing another form, another variation that would induce the absorption rate. This way we can get even higher acceleration rates, but still stay below that glass transition temperature. So instead of mimicking 5 to 10 years within a month, we could, depending on the material again, we could mimic something between 10 to 20 years or even higher if we let the material soak in this water for longer. And in the next slide, we have another equipment that was added recently to the lab, which is a dynamic mechanical analysis machine called DMA. So we can do material characterization between negative 150 C and 600 C. Also, the loading rate is up to 200 hertz. And what that would translate to in terms of strain rate depends on the geometry of the material. But we essentially can do a strain rate sweep. So we can start at quasi-static loading and go up to 200 hertz, and that would give us a dynamic performance of the material, and we're getting stiffness as well as any viscoelastic behavior of the material. And this complements the split Hopkins bar because we're getting only the elastic properties of the material. The split Hopkins bar, we're mostly getting the large deformation or the plastic deformation of the material. So between these two equipment, we can get a robust material model for a wide range of temperatures and loading conditions. And in the next slide, we can also do some composite manufacturing in our lab, mostly in a smaller scale than many of the companies that are here. But if we're talking about experimentation size specimens, so we could make our specimens for experimentation and then test and characterize them and test them ourselves. We can do the vacuum infusion using fabrics and some liquid resin, or also just fill them from prepregs. Right now we're mostly doing flat specimens, but we can also do tubes by roll wrapping prepregs, or curved specimens if there's a mold for it. And I think that sums up the most of the capabilities in the lab. We do have some variations of many of these equipments. But I'll be happy to answer any questions. I think the questions are later on, correct?
Yep, we'll hold the questions until the end.
Okay.
Let me unmute here. Sumanta, are you now unmuted?
Yes. Can you hear me?
There you are. Yes, thank you. Yes, we can hear you.
Sure. Yeah, so this is my information. Can you go to the next slide, please? Okay. Yeah, so first of all, thanks everyone for attending today's webinar. My name is Sumanta Das. I am an assistant professor of civil engineering at the University of Rhode Island. And today I'm presenting some of our recently completed and ongoing research works at our multi-scale and multi-physics mechanics of materials research lab. And so our lab performs multi-scale and multi-physics computational as well as experimental work. And we complement the experimental facilities or experimental research going on in DPML. So we work in close collaboration with DPML in many of these projects. Can you go to the next slide, please? So here are some of our visuals from our lab. We are located in the second floor of URI's new engineering building. And here I'm showing various materials characterization and performance evaluation equipment that we have in our lab. And so overall, we have various small scale, means micron, nanoscale experimentations, chemical property evaluation, as well as mechanical property evaluation equipment that can probe the material structure at different length scales and evaluate the properties. Next slide, please. So I'll start this presentation by acknowledging our students. All our research works and plans will be incomplete without their hard work and dedication. So I should start this presentation by acknowledging them. So we have graduate students, both masters and PhD, and undergraduate students working on various projects in our lab. This photo was taken last year during the fall semester. When we moved into the new building, we were all excited, and everything was normal back then. So yeah, we were just posing there as a group. Things are a little bit different now. We have to maintain different aspects of social distancing in the lab. So we have all those plans in place. Can we go to the next slide, please? Okay. So in this slide, I have tried to summarize our materials design strategy in M4RL. And it has three main integrated components, as you can see here. The first one is multi-scale and multi-physics modeling, where we model multi-physics behavior at various length scales spanning from atomic scale to large macro scale. We perform analysis for thermal, mechanical, electrical, and various combinations such as thermomechanical, electromechanical, and thermo-electromechanical analysis. And in addition to modeling, we also perform various multi-scale experiments. Overall, we follow an integrated modeling experiment and machine learning based integrated approach, material design approach, where each of these three components, modeling, experiment, and machine learning, they mutually inform and advance each other. So in the next slide, I'll show some recent work example of these three components that we have done. So in the multi-scale modeling, we perform analysis at multiple length scales, starting from atomic scale to nano, micro, meso, and big macro scale. We adopt different techniques at different length scales to increase our efficiency of material design. At atomic scale, we implement molecular dynamics and density functional theory. In the middle scales, we can apply periodynamics, discrete element method, finite element analysis, etc., depending on which problem we are tackling. And also at the large scale, we perform finite element analysis and extended finite element analysis, or XFEM, if we have crack propagation or if you're trying to model the post-peak behavior of composites. So generally, composite materials show different structures at different length scale. So if we zoom in different locations at different scales, we find different structures. And we can tweak these material structures at any of these length scales that are shown here. And that will reflect in the macro scale performance of the structure that are made from composite. So we tweak different material structures and material properties at different length scales and come up with the optimized design. So that is how we implement multi-scale analysis in our materials design process. In the next slide, I am showing some of the examples of multi-scale simulations to make this clear. Not this one. Yeah. So here I am showing, here I'm showing the examples of different simulations, multi-scale simulation at different scales. We can see the atomic structures at atomic scale. Micron scale, we apply composite micromechanics. We do mesoscale modeling. We work on woven textile reinforced textile composites. And at the same time, we also model macro scale performance under different type of loading conditions. And all these scales are interlinked and they mutually inform each other, advance each other, give feedback. And that's how this whole integrated approach works, where we link all these different length scales and finally go to the macro scale to go for performance evaluation of the material. Can we go to the next slide, please? Yes. So here, the previous slides I have shown the multi-scale simulations or computational modeling approach. Now, in these next few slides, I'll be showing multi-scale experiments that we perform for our material design studies. Next slide, please. So here are some examples of some 3D pictures of a particulate reinforced matrix that is imaged using high resolution X-ray tomography. Here we can see the distribution of toughening particles, and we can check whether they are distributed properly or not. We can calculate the volume fraction of different phases through 3D image analysis. And these features are very critical in optimizing the material structure. Also, these real 3D images that we obtain from X-ray tomography can be further discretized, and we can use it for finite element analysis at different scales. So this is how we couple our experiments with simulations fundamentally. Next slide, please. So here I have shown another piece of equipment that is micro indenter. If we have a material like composite where we have multiple phases, this equipment can indent these multiple materials within the composite or multiple phases in micron scale and can evaluate their properties separately. And these micro indentation experiments help us evaluate the micromechanical behavior of composites. And the results also serve as input for the modeling because we obtain the component properties for any composite through this indentation. So here we have a diamond tip that indents different phases with the composites and gives us the behavior or the performance of those intrinsic phases that are in the composite. Next slide, please. So here I have shown various multi-scale materials characterization equipment that are there in our lab. So we have thermogravimetric analysis and differential scanning calorimeter that evaluate the chemical and thermal properties of materials. Also, we have electrical impedance spectroscope, EIS, that can perform electromechanical experiments for strength sensing along with a load frame. We have the laser diffraction particle size analyzer, and we use that for our research work on multifunctional composites, where we add different additive particles in the matrix for various multifunctional reasons. And for the large scale, so these were all small scale experiments. And for the large scale experiments, such as split Hopkinson pressure bar, shock tube, and other experimental facilities previously shown, we directly collaborate for those with DPML and to evaluate the macro scale performance. So our collaboration, that's our collaboration with DPML completes our overall strategy of experimenting on the material structure at different length scales, micron, nano, micro, meso, as well as macro when we collaborate with DPML. Next slide, please. So this slide summarizes our approach, multi-scale experiments, and we can see that multi-scale experiments and modeling work together generate large data set, because if we have to generate, say, 10,000 data points or 10,000 experimental results, or if we have to evaluate 10,000 different combinations of materials, doing only experiment will be not efficient. However, we need experiment to validate our model at certain extents. So that's how we generate those large data or large combinations using our multi-scale simulations. And at the same time, we supplement with the various small scale experiments as well as the macro scale experiments. And together with modeling and experiments, we generate this large or big data. And that big data, we use that in different machine learning algorithms, such as neural networks or Gaussian process regression. We apply those algorithms to arrive at optimized design of materials. And as I mentioned before, these three components, experiments, modeling, and machine learning, they are interconnected. They mutually inform and advance each other. And this coupling makes sure that we are not using machine learning as a black box. So our machine learning is advanced or is driven through fundamental laws of physics that we apply through our experiments and the multi-scale simulations. So that is how we make sure the fundamental laws of physics are maintained, and so that we do not use this machine learning techniques as a black box. We use it very comprehensively and fundamentally. So in the next slide, I'll show two of our recent industrial projects that we collaborated with DPML. The first one is the recent work we collaborated with that we did for Goetz Composites. And in this project, we designed composite pressure vessels through our multi-scale and experimental combined approach in collaboration with DPML. And we have designed this to withstand full ocean depth pressures. So here we have designed it for almost 9,000 or 10,000 meters depth so that it can withstand at that pressure. The other work that we did recently was this work with Nautilus Defense. And here we have designed a smart composite for health monitoring. So these are the two recent examples of our collaboration with industry, and we did this with DPML, and we collaborated with Helio and Professor Shukla. So in the next slide, few slides, I'm gonna just explain some of our ongoing research works. And these are only the ones that I'm mentioning. These are related to composites, but we are working on other materials as well. So these are some of the some portions of our overall research effort in the lab. So we are working on nano-engineered smart composite materials, design of composite materials subjected to different types of high strain rates. We are working on 3D printed composite materials for impact mitigation. And we are also working on designing more environment-friendly, smart and multifunctional, bio-based, 100% plant-based polymer composites. So these are the some of the four of the works that we are working on right now. And I'm going to explain some of those little bit briefly in the next few slides. So the first slide, this is the work that the field that we are working on is nano-engineered smart composites. And this is the paper that we recently published in Composite Structures. In that we had placed carbon nanotubes at different strategically placed hierarchical length scales to achieve good strain sensing efficiency. And on the similar line, we are also developing other nano-engineered composites from this combined experiment, modeling, and machine learning based approach. Next slide, please. So we are also working on designing composites subjected to various dynamic loading conditions. And here we directly collaborate with Dynamic Photomechanics Laboratory. In the example that I'm showing here, this is one of the ongoing works that we are working on. Here I'm showing this example where we are designing composite cylinders for underwater shock loading. And here the design is performed again with probing the hierarchical structure of the composite and then generating large data and performing machine learning. At the same time, we are getting experimental input from DPML. So that's how we have this integrated approach to design these composite cylinders. Next slide, please. So we are also working on 3D printed composites for enhanced impact mitigation. Here I'm showing some of the core materials that we are printing with different core composites that we are printing with different materials, and this will be used as core in sandwich composites. And here these kind of core materials we're developing so that it can give us enhanced plastic deformation and energy absorption, so that we can optimize its impact mitigation characteristics. Next slide, please. So another interesting topic that we recently started working on is 100% bio-based composites that are developed from renewable resources with eco-friendly manufacturing process. And these materials are fully biodegradable. So we are investigating on how these 100% bio-based composites can be engineered so that we can enhance their engineering performance for all more common scale applications. So with that, I will end this part of the presentation, and thanks again for attending this webinar. And I'll now pass it on to Mary.
Yes, thank you. Thank you very much. If my panelists could unmute yourself and turn your screens on, that would be great. And Susan, why don't we bring the slides down so that we can have their faces up. And I'm going to start with Catherine Flynn, who joined us at very last minute notice and also has to leave to run to another meeting. So Catherine Flynn is the Executive Director of the University of Rhode Island Business Engagement Center. Catherine, could you give us an example or two of, oh, don't have sound yet, hang on.
Okay, there we go.
There you go. All right, thank you.
I couldn't unmute myself. I think you guys have the controls.
Yes, we have control on that. Can you give us an example or two of successful research collaborations between a company and URI?
Sure. So just for those of you who are not familiar on the call with the University of Rhode Island Business Engagement Center, the Business Engagement Center is just about 8 years old now. We've been we were created, I actually modeled the Business Engagement Center when we opened it after University of Michigan, who had started their Business Engagement Center maybe 10 years ago in their engineering school. So it's appropriate that we're talking about engineering here. Engineering and industry, or the engineering colleges in general and industry, tend to have very good symbiotic relationships, and that's no different here in Rhode Island. And so we've, over the years, had a lot of great partnerships with our industry partners. Some of them have been mentioned already by our faculty members who, as they were talking, I realized they're way smarter than I am, and they have got a lot of really fantastic stuff going on. But specific to the materials world, since that's what we're talking about here, we did some work for Cooley Group, taking some of their textile materials and weaving sensor materials through it. We've done work for Navitec on the research side, which is where George, my colleague, has now gone. But we were with them, we were working on testing the implosion of their material. We also, outside of materials, we've done a lot of work in engineering with wind turbine companies, and they're a small company that got an innovation voucher, CBC Wind. They were testing their wind turbine actually eventually down on our Graduate School of Oceanography campus. So they got a lot of research done with us, and then they went ahead and tested the turbine down there. The partnerships that have been the best are the ones where there are opportunities for students and faculty and the company to work together. And often, in the case of one we had with Hope Global is a textile company up in Cumberland. They thought that if they changed their spools, they might be able to reduce waste in their factory. So they brought it as a capstone project to our mechanical engineering school. And the change that they made was so successful, they saved around $400,000 a year in just purely waste. And they ended up hiring the 2 students who worked on the project for them. So it's a great, it was a great opportunity for the students to solve a real world problem, and they got jobs, and it's the company ended up saving money. So that was sort of a win-win, I should say. Mm-hmm. And in the case of companies like Navitec, we're now taking it to the next level and working with them on a couple of federal possibilities. Other companies we've done SBIRs with. So having a sort of industry university relationship or research can end up taking many forms, but hopefully that answers your question about a few things that we're doing.
Sure, yes, thank you. Could you also talk about the other reasons to work with URI and beyond the research and technical capabilities?
Well, I mean, the number one answer to that is talent. We have students who are anxious to work in industry. They're anxious to work with industry, as I said, on real world problems. So obviously accessing the university on the talent front is one way. Another example is we're doing right now some significant training at URI for Amgen for their employees. So professional development, where the employees are doing, rather than being in the factory being trained, they're actually being trained at URI, and then they can go work in the new Amgen factory. So besides the research enterprise between our talent, the potential for professional development for our industry partners, as well as the equipment. I mean, you just heard on the panel all the different incredible equipment that we have at URI. Especially small businesses, they just can't afford to have this equipment. So for us to be able to give access to the equipment in our labs to the smaller businesses, it's a great opportunity for the companies to come and engage with us.
Great, thank you, Catherine. I know that you are
I can stay actually a little longer than 4. I kind of moved things around, but so I'll stay around for questions if necessary.
Okay, great, thanks. I'm going to move on to Christian. Christian Cowan is the Chief Operating Officer of the University of Rhode Island Research Foundation and the Executive Director of the 401 Tech Bridge. Many of you know Christian from his role as the Center Director of Polaris MEP, and I would be amiss if I didn't say that without Catherine and Susan and Christian and Secretary Pryor at Commerce, and Steve Bardnaro, who's on the call here at Newick, and a bunch of folks at Newick, 401 Tech Bridge wouldn't exist. It's really been their vision for the last 3 or 4 years. Also Wendy Mackey, who's not here today, to really inspired by the work that all of you do to find ways to serve you better and to continue to make it easier to commercialize and advance your technology. So with that, Christian, I would ask, why is it important for companies to invest in research and R&D?
Well, thanks for the introduction, Mary. I appreciate it. So every company that I've worked with and for has a significant investment in R&D in order to look into the future, protect their business, and make sure that they're analyzing the technical landscape and the markets that they serve. Research and development support has always been a focus of mine personally in Polaris. We had the unique opportunity of starting 401 TechBridge to very specifically make sure that companies are better equipped to invest in R&D, so they're paying attention to their future products and the future progression of their business. It's been a fun journey with 401 TechBridge. Programs like this were always in our sights. We've always looked for ways to better connect industry, academia, and the government. As Steve mentioned, Steve Bonaro, who's been absolutely critical on the Navy side. So this is an interesting opportunity to better connect industry into, my opinion, are the best university in the state and in the region, the incredible talent at URI. And it's intended to, from an R&D standpoint, really be a bridge and a connector, not to solve all the R&D problems, both with academia and with industry, but to serve as a connector, as initial spark connector, as well as in partnership with other programs like the state innovation vouchers and with programs coming out of Newark as well. So research and development completely critical for technology-based companies today.
Great, thank you. You talked about this a little bit, but could you expound a little bit on the benefits to a business of partnering with both 401 TechBridge and the universities, rather than going, not that we want to cut Catherine, we're the introduction to Catherine into the Business Engagement Center, but can you explain a little bit about what the benefits are of taking that pathway rather than going directly to the university?
Sure, there's been, I give an incredible amount of credit to Catherine, who's on the leadership team at URI, and President Daly at URI for really knocking down barriers as the years have gone on from an industry collaboration standpoint. So connecting industry into URI is critical to leverage the resources there that may not be available in a company. But there is a larger ecosystem for sure. There are more connections, more programs, more partners that can help progress a company's business based on technology. The business school at URI can certainly be part of it, but 401 TechBridge has other partners that can help push forward commercialization efforts, market analysis, pricing analysis, go-to-market strategies, et cetera. The technology innovation and productization of that technology is the first step. Bringing products to market is a bigger picture and things where a lot of the 401 TechBridge partners can help.
Great, thank you. I'll just add a quick example there that we had a call the other day from a company that was looking for a specific test. And I reached out to URI, who does not have the capability. This was for a PPE product. Called the office at UMass Dartmouth, who did not have the capability either, but they introduced me to Roger Williams University. And Roger Williams didn't have the expertise, but they referred me to somebody at Brown. So within the course of about 4 days, we were able to find the resources that were available, which helps save a lot of time. I think you're all very busy people, and if we can help do that legwork for you, then we're happy to do that and to help you run down resources and connect you as necessary. I'm going to move on to, in the interest of time, to Susan. Susan Daly is the Vice President of Strategy at the Rhode Island Marine Trades Association. She is a strategic advisor to the 401 TechBridge. She also works closely with the Rhode Island Composites Alliance. And again, very instrumental to, especially working with the congressional delegation over the years, because Senator Whitehouse and Senator Reid have certainly been big supporters of ours over the years to help move 401 TechBridge forward and line up a lot of the original funding. Susan, what are the challenges and the hurdles that small businesses face as far as doing research and development?
Thank you, Mary, for the intro. To your question, actually both Catherine and Christian have, sort of mentioned a few, but the R&D process, one can be from concept to product, can be quite a long one and often take years. And as a small company, you may be not able to either justify or invest in the required resources to be able to do that in-house, or dedicate a resource to that. And, you know, that means people, that means money, that means time, and it means equipment. And, but at the same time, it's strategically important to invest in it. And particularly in these sectors. So I think finding efficient and impactful ways to do research, such as what we're going to, you know, talk about here shortly with the Manufacturing Innovation Challenge. You know, it's really there to help all of you find a way to shorten down that R&D cycle and the timeline so that you can get from concept to, you know, product to market more quickly. But I think another challenge that is tied into that too, and especially, you know, a number of you on this call, you certainly have experienced it, is, you know, sort of how do you prove to your customers, you know, the value and the legitimacy of, you know, some of the solutions that, you know, and what can be perceived as better solutions using new materials. And, you know, this is particularly a challenge and an opportunity with customers who've been working with traditional materials for a long time, like steel and concrete. So I think having the opportunity to have third-party independent research and testing, you know, really has a way to be able to demonstrate and validate, you know, what your product and your solution, and figure out how to actually be able to say, it's not just we believe, but here's the proof, here's how we can do it. So I think that's, you know, absolutely critical here.
Thank you. I mean, I know you would like to build a little bit on Catherine's answer in terms of, besides the results and outcomes of the research that they're doing with the university, how else are companies benefiting from working with URI?
Well, I certainly want to echo what Catherine talked about in terms of access to talent. It really, when you do it, it's a great recruiting platform. And I think it's also a really effective way for a company to scout for new employees, because you get you get an in-depth look at what the graduate and the undergraduate students do in terms of working with them on, and, you know, the skills you're looking for, both technical, but, you know, how do they approach problems? How do they work in teams? I mean, it's just, it's probably one of the best recruiting screeners you can have. But I also think that what a business gets by working with, you know, URI or with a university is they get a voice, and they can bring that voice to the table in terms of the types of problems and opportunities and challenges that business are facing out in the real world. Not to say that URI is not in the real world, that's not fair, but, you know, really you've got a seat at the table to talk about what's important to you. And as part of that, you really can help shape, I think, how URI is focusing on what the students are learning, help, you know, have some impact into the curriculum to make sure that a lot of that is sort of on the front edge, which in turn means that the students are learning what's, you know, relevant and forward-looking, which benefits you. So it's almost like a circle that, you know, sort of helps to, you know, promote itself as it goes.
Great, thank you. I'm going to move on to Eric Goetz. Eric, can you unmute yourself? Do you need me to do that? Let's see if we can.
Good, you had him.
I had him. There we go.
Okay.
Okay, here you are. Eric Goetz is the founder and chief technical officer of Goetz Composites. In 2008, Eric's company was making boats, and the economy tanked, and he had a tough decision to make about what he was going to do with his company, and they rebuilt it by pivoting in a completely different direction. Throughout that time, he has been I say a poster child of what the value that 401 TechBridge brings to companies, in that every time Eric walks into a room, he seems to walk away with a new piece of business. And the ability to understand the connections and ask for help when he needs it with different projects, and ask for introductions, has been of benefit to their company. So Eric, I'd just like to ask you to talk a little bit about the research projects you've done at URI, but also I know that you've worked with a lot of other academic institutions in the region. Why URI, and how has it benefited Goetz Composites?
Well, one of the things that URI has, which other institutions don't have, is a way to, they have a framework, a business framework that makes it pretty easy to work with URI. And certainly, you know, we want to engage with the professors who are going to direct the research, but before you get to work with the professors, you've got to work on a relationship, a business relationship with the university. And through Catherine's office, a lot of that business interaction is streamlined, and that makes it easier for us and for anyone else who engages with URI to create the engagement and to move forward without wasting a lot of time, without wasting the professor's time on dealing with the business side of the transaction. So one of the really great things is the university as a whole, as I've said before, they get it. They get the fact that there is business that needs to be transacted before people go in the lab and slice and dice and figure things out. So that's one of the things that really, I think, sets URI apart. And also for us, and in our dealings with various topics in the marine sphere, there's a lot of experience there, starting with Arun, and then we're working on several projects, you know, with Sumanta and Helio, and they get the fact that this isn't just research for research's sake. This is research so that we can then take their results and develop different pieces of equipment or product or whatever we're working on. So that, to us, creates a lot of value. And that's really why URI stands head and shoulders above some of the other institutions with whom we've worked.
Great, thank you. From your experience in working with the university, what should a company be prepared to do in order to get the most out of their project?
Well, I mean, first of all, have a clear idea of what it is you're trying to accomplish. If you can have a clear idea, then you can successfully communicate that with not only the business side, so that you get the business out of the way quickly, but also with the professors who are going to either do or direct the work that needs to be done. And then the second thing you need to do is allow the professors the time that they need to get the work done, and they're not. I mean, basically, they work quickly, which is really, really great, because in business, we often don't have time to just wait for results to come out. So one of the things that we really like is Helio and Sumanta do not fool around. They get the work done and they get it back to us, and we can then get back in the shop and make stuff. So those are some of the important features that we enjoy.
Terrific, thank you. We just have a couple of questions for the faculty, so I'm going to cycle back and do those now, and then I will explain the process for applying for the Materials Innovation Challenge. Arun, going back to you, there was a question about how cold for the experimentation. Oop, I'm going to have to unmute you, hang on.
Okay, I guess now you can hear me, right?
Yes.
So for the cold temperatures in our lab, we have, as I said, a range of temperatures that we can do. They start all the way from the Arctic temperatures, -50, -40, -50 degrees Celsius, to very high temperatures of 1,000 degrees plus 1,200 degrees Celsius. So it's a huge range, depending on what kind of experiments that we want to do. So that will also depend on that. But this range that I'm giving you is for different equipment. So again, for composite materials, for example, I don't think we need to go to very high temperatures, because the matrix materials get soft very quickly. But those kind of ranges are available in the lab.
Terrific, thank you. And Sumanta, the question for you was, with the materials printing, does URI have the capacity to do nanoscale at 2.5D or 3D?
We do not have nanoscale capability in terms of printing as of now, but we can print with nano particulates or nanofibers with the composite. Certainly, we can go up to micron size resolution as of now, without printing.
Terrific, thank you. Christian, this one's for you, so let me unmute you. Buttons don't want to work today. There we go. All right, we got you off. How open is the 401 Tech Bridge to early stage entrepreneurial startups that have promising technology but do not yet have profitability in commercialized products? And if it is, would the URI Tech Transfer Office get involved in possible IP development with the startup?
Yeah, I mean, early stage startups, people with ideas, technology ideas, and productization plans on that technology is clearly something that we're strategically trying to support better. And there's a host of different capabilities that 401 TechBridge has to support that, as well as partners that we're able to bring in. Intellectual property has been one of the places we're focusing on, making sure that the industry partners are able to own the intellectual property, commercialize it. The technology is no value to an industry partner if they can't make money on it. So we're focused on making sure that the industry partners are able to take advantage of that. The Intellectual Property Office of the University of Rhode Island is essentially our parent organization, so we've got the ability to pull in resources there. And there are certainly a lot of other state programs that we're strategically partnered with to be able to support the startup companies a little bit better, including Mass Challenge, Venture Mentoring Services, the I-Corps program, RIHub, which is the incubator innovation campus that's in Providence. So there's a host of startup facilities, capabilities, and partners that we're able to connect to startup companies. So it's clearly in our wheelhouse of trying to make sure that we support those partners better and better.
Excellent, thank you. Catherine, do you have anything to add to that one before we move on? No, okay. Was that a yes, but you need to unmute, yeah.
I'm getting really good at Zoom sign language.
Yes.
Yeah, I mean, we're always happy to work with entrepreneurial startups. We work with people from, one-person companies all the way to thousands of persons companies. So I'm happy to help in any way I can with connecting these companies into URI and finding the purpose behind the Business Engagement Center is to make the pathway from industry into the right place at the university seamless. And so that's we're like the concierge. So I'm about to put my my email into the chat box. So for those of you who don't know me or don't know how to find me, I can, you can now this way, but I do unfortunately have to go at this point. So.
Okay, great. Thank you very much, Catherine. And Susan, if we could head back into the slides, I will spend the last few minutes talking about the procedures to apply. And then at the end, if anyone has last questions, please add them to the chat. So the Materials Innovation Challenge has an award pool of $105,000. The awards will be up to $35,000. It will depend. We kind of looked at the range of the typical projects in the lab, and we understand that some of you may just need some testing or validation. Some of you may need bigger projects, so we're trying to be flexible with the award amount. And the funds will support the research at URI. It will not pay for your expenses or internal R&D. Next slide, please. The process is, as you heard Eric say, and being able to talk through what the project is and make sure you're in alignment is a really critical first step. So we're going to start the process with having you call me to set up an appointment with the faculty to discuss your project to make sure that it aligns with the capabilities of the lab. And we will be doing those in the next couple of weeks. So you can email me at the address below. I will also add my other email address into the chat. My email is being migrated over from Polaris MEP to 401 TechBridge tomorrow. And so I would ask that you email me at both addresses just to make sure that you don't get dropped in the migration. These meetings will happen via Zoom, and they will occur before you submit an application. That will just make it easier to make sure that when you submit an application with a budget, with a project scope, it has been vetted, you know, that the university is in alignment with it and the fees are accurate and all that kind of thing. We just want to try to make it as streamlined as possible for you to submit something that the review committee can look at and actually review without a lot of questions. Next slide, please. We are using the University of Rhode Island portal, the InfoReady portal, to collect the proposals. When you go to this website, the URI infoready4.com, you will need to set up a user account, because primarily this is used for internal academic applications. It does allow outside users, but you will need to set up a username. When you do that, you will be able to choose the proposal and take a look at it, and then re-log in and come back and forth as you continue to build out your application. And all of this will go out when we send out the slides, and I also will include an email that includes the link so that you can read through the proposal requirements, as well as have a link to where you can register your account. Next slide, please. The application period closes on October 26th, so that I would not delay in giving us a call if you're interested in proceeding, so that we can get your appointment set up with the faculty. We will be accepting applications through the 26th and then reviewing them in November with an anticipated start date after the first of the year of the projects. In some cases, there may be opportunities to start the projects a little bit early, but it will be late November before we make awards. Next slide, please. So the requirements are going to be a written project description of no more than 5 pages. Again, we don't want to put a lot of requirements on top of you. A profile of your company, your markets, your expertise of your key staff, the need or market challenge that you are trying to address and the potential, the innovative idea behind the project, and the impact it will have on your business. I would say a couple of things on this. If you are collaborating with a group of companies or more than one company to do an application, please include profiles of all of the companies that are participating. It's certainly fine if you want to team up and do a project together. If there's something that might be of benefit to all of you or to a number of you, please continue, or please consider doing that. Let's move to the next slide, please. You also will need to identify which of the which lab or both labs, so that we understand who you want to work with and why it's important to use their expertise to the success of the project. This can be fairly short. You've been introduced to the faculty. We know who they are, working with URI as much. But I would also ask that you include information on the key project personnel. And again, if you're working more than one company is collaborating on the proposal, please include the key project personnel from each company. Next slide, please. We would like to see a budget. That would be the a budget for the entire project, the equipment use rate, the materials and supplies, the personnel, the amount of the budget that you're requesting from the Materials Innovation Challenge. And again, that would be the amount that would cover the project at URI. And then let us know what the additional sources of funding are that are supporting the project and your expenses, whether that's in kind or other funding that you have available. Next slide, please. The panel review will happen in late October through November, and the awards will be announced, and we will go through the contracting process in late November and December, and again with projects to kick off the 18th, or I'm sorry, to kick off once we get into January in most cases. Next slide. I think that may be all of them. So again, the summary, contact us to schedule an introductory meeting, create an account. You can go ahead and create the account before you actually have the introductory meeting if you'd like, so that you can review all of the application information. Complete and submit the application before October 26th. Don't hesitate to reach out to me with questions. Susan and I will be doing most of the follow-up if you need technical assistance along the way as you're putting your proposal together. We will also be the people connecting you into the university. As we mentioned earlier with George Nicolopoulos leaving just within the last couple of weeks, Catherine has a lot on her plate to cover both George's job and her own. And so Susan and I are going to handle some of the connections within the university to keep the process moving without overburdening Catherine. There is, all of this will go out via email so that you will have it. It will also be on the 401 TechBridge website. So if you have colleagues who are not here today, they will be able to watch this webinar, look at the slide deck, and also continue. It's not a requirement that you attend today in order to proceed into the next steps of the competition. Something that comes up a lot is because of our relationship with the Naval X Northeast Tech Bridge, people ask if we just do projects that relate to the Navy. The answer is no. If you have other projects that you're pursuing that are not DoD related or are related to a different branch of the military, certainly that will be it's fine. We want you to focus on the projects that best meet your needs, and that help propel your technology and your business forward. Somebody said that they see 401techbridge.com and .org, and that's my proofreading error. I apologize. It is 401techbridge.org, and I will clean that up in the slides before they go out. And if we have any other questions, I am happy to take questions, or we also still have the faculty here and the rest of the panelists. Susan, do you want to bring the screens back up? We are just about at 4:30, so I will hang for a couple minutes if people have questions. If you do not, like I said, don't hesitate to reach out to us as you get an opportunity. We hope that you will all consider participating in the program, and it is a competitive program. There will be a review process. We do anticipate that we will have more proposals than we have funding for. That will become motivation for us to go out and find more funding so that we can continue programs like this. And also I would say, if you meet with the faculty and you determine that this group of faculty is not the best match for your project, you would not be eligible for this funding, but certainly through 401 TechBridge, we would help you find faculty either at the University of Rhode Island or one of the other universities in the region to help, or any other opportunities that there may be to help you move your ideas forward. I would like to thank you all very much for joining us today. If there aren't any other questions, then I will thank you all, and you can all leave the call.